reaction mechanism. Reaction mechanism can be a single step or multi-step. If it's single step, then the reaction mechanism only consists of one step, as illustrated here. And in actual fact, that equation is also the stoichiometric equation. However, in the case of multi-step, say for example, if the reaction mechanism is in 2 steps, then you can actually have a case whereby the stoichiometric equation is x plus y gives z. In the first step, x is converted to a, and then a plus y will then give z. If you take the first step and the second step and you add together, it will give you the stoichiometric equations. That's the difference between a single step reaction mechanism and one that is multi-steps. The next important thing in the reaction mechanism is to identify which one is the rate determining step, RDS in short. Rate determining step or RDS is the slowest step among all the steps that takes place in the reaction mechanism. And from the rate determining steps, we are also able to derive the rate equation. Let us take a look. So in the single step example that we covered, 1x plus 1y give 1z. So the reaction only has one step, which is also the slow step in this case, which means during the rate determining step, it involves 1x and 1y. Therefore, because of this, the rate equation is r equal to k con x to the power of 1 and con y to the power of 1. So the rate equation is the order of reactions within the rate equation is in fact related to the stoichiometric constant of the rate determining step. Let us now take a look at the multi-steps reaction mechanism. So in the multi-step, the first step is also the slow step, which means one of the X molecule is converted to A. In this case, if the rate determining step only involves one X, then the rate equation will only involve the concentration of X. Hence, R is equal to K con X. And in this case, it's raised to the power of 1, or the order of reaction is 1, because in the stoichiometric constant of the rate determining step, it involves only one X. Finally, we can also explain whether reaction is bimolecular or unimolecular. So in the first step of this example, it is bimolecular because it involves 2 molecules, which is actually X having to collide with Y. In the case of this example that we have, in the rate determining step, it involves only one molecule. So in this case, it is described as unimolecular. So let us take a look at more examples. In this first example, the first step is the slow step, the second step is the fast step. So you can see that when you add the first step and the second step, you will end up with the chemical reactions as such. We could also know now why the reactions is 0 order with respect to the concentration of OH minus, because in the rate determining step, it only involves one Rx. So like we explained earlier, if you have the rate determining step, you can now derive the rate equation, which only involves the reactants in the rate determining step, which is your Rx. And since only one Rx is involved, the order of reaction with respect to Rx is first order. The reason why OH minus is 0 order in the reaction is because that OH minus is only involved in the fast step. So no matter how high the concentration of OH minus is, step 1 is really slower than step 2, which means the overall reaction rate is actually driven by step 1, which is the rate determining step. So no matter how you increase the concentration of OH minus, it will not make the entire reaction faster, since the slow step is still step 1, which is the rate determining step. The next thing that we want to bring up, R plus is produced in one of the steps of the reaction mechanism, but subsequently R plus does not manifest itself as a product. So R plus can be termed as an intermediate or transition state. Let's now give example to illustrate the difference. So in this example, we'll now take a look at the energy profile. In the energy profile that's illustrated here, it mirrors that of your reaction mechanism given here. Since the first step is slow, the activation energy would actually be higher for EA1 relative to EA2. In the second part, we need to state that R plus is in fact an intermediate. Because it's an intermediate, you can see that that is the way that we actually sketch it. Later, we'll give an example where we actually involve a transition state. So hence, in exam, if you are given an energy profile, from the energy profile, you also will be able to identify that which step is the rate determining step. Because in this case, step 1 will be the rate determining step because the activation energy is higher than the second step. And the next thing to pinpoint as well is to know that R plus is an intermediate. Let's take a look at another energy profile diagram. In this example that we have, we know that ROHX is a transition state. It's not an intermediate. So in this case, if you look at the reaction mechanism, Again, in the same vein, you see that ROHX is actually being produced in one of the steps, and subsequently ROHX is being converted to a product. So ROHX is not a product at the end of the reaction mechanism. So ROHX is in actual fact a transition state, and if it's given a transition state in terms of the energy profile, it should be drawn in this manner. Transition state means that it's not stable and it cannot be isolated experimentally. So in terms of the energy profile diagram, we can see that for step 1, this is actually the EA1. And for step 2, in actual fact, the EA is 0, because as you can see, the transition state just converts to the product in the second step, which means that in actual fact, for the second step, the activation energy in the second step is in fact 0, which is the reason why the first step is still the rate determining step. And based on the sketch itself, ROHX, which is actually at the peak of the energy profile diagram, actually indicates that it is a transition state. Finally, we'll now take a look at what happened when the second step becomes the rate determining step. Thus far, all the examples that's covered, we have the first step as the slow step with a higher EA and therefore the rate determining step. So in the case whereby the second step or the third step is the slow step, we need to bear in mind that any step that precedes before it becomes reversible. Let's explain why. Let's explain with an analogy. So say for example, A is able to pass the parcel to B very quickly, so it's very fast. Okay, while C will pass the parcel to D very slowly. So in this case, what happened is that when B started taking the parcels, the B will have to start placing the parcel down because C is actually taking them very slowly. So after some times, the parcel will be stacked up, and you will find that B will have no choice to start to have to take the parcel and give it back to A because there's no more space to accumulate the parcel. So based on this example, what we are saying is that if the second step is actually the rate determining step or the slow step, any step before it, the first step in this example, will actually be a reversible reaction. Even though in the equation they did not state, you can safely assume that the reaction would have to be reversible. So let us now take a look at this example. In this example, X plus H plus gives you XH plus, so the reaction is fast. XH plus Y gives you actually Z plus H plus. This is the rate determining step. So since the second step is a slow step and it's the rate determining step, we can right away derive the rate equation. In this case, we express the rate equations in terms of reactant, XH plus and Y, and express to the power of 1, since that is actually the respective stoichiometric constant. One of the things that we do note is that RH plus in actual fact is not a reactant. You will learn that in the initial part when we cover rate equation, we state that in rate equation, we express rate equation in terms of the concentration of reactants. Therefore, because of this, we cannot finalize the rate equation as such. And upon the closer look, you also notice that in fact SH plus is actually an intermediate. As this is actually the chemical equation, where in this example, what is interesting is that we know that XH plus, H plus in actual fact is a catalyst. So how do we now manipulate this rate equation to one that whereby the rate equation is expressed in terms of concentration of reactants? The way to do that is to examine your step 1. So step 1 holds the key to it. As explained earlier, even without being told, you will know that if the second step is the rate determining step, the first step will have to be reversible. Since the first step is reversible, as indicated here, we can now have a Kc expression of it, whereby Kc is an equilibrium constant. So the Kc is a constant value, which only changes with temperature. So making SH plus the subject from here, we can actually now substitute this expression into here. So from this, we can derive the rate equation, which is expressed in terms of Conx, Con H plus, and Y to the power of 1, and Y. And this is actually the final rate equation, which informs us that the reaction rate of this reaction that we studied is dependent on the concentration of X, concentration of Y, and as well as the concentration of the catalyst H plus.